Hello everyone. This is hopefully a shortish video, an optional video, overlooking some basic math needed to really understand some of the chemistry concepts in a general chemistry class. So although we won't be requiring calculus, some of the equations are derived using calculus and other types of math. So I think it's definitely sound advice that any student in general chemistry pick up a little bit of basic calculus as they go. So again, this is intended to be a brief introduction to some calculus concepts for a general chemistry audience. So we'll start off with differential calculus, and I'll, as usual, make these notes available to my students as a PDF. So let's see what Newton did all those years ago. So if we start with, there we go. If we start with a graph here, we've got a line. You can see the straight line here with 2 points indicated, point P and point Q. We can label the y-axis as some function, a function of x, and we have x plotted on the x-axis. So x, whatever x is, and then a function of x on the y-axis. Okay, let the point P be at x0, where 0 is just the label, and then let the point Q be at a point x0 plus h. So that just means the distance between x at 0 and this point is h, where h is just another label. On the y-axis, let P register a y value of f at x0, so it's whatever the functional value is at the point x0. And obviously, at q, we have f at the point x0 plus h. So hopefully that graph, the way it's interpreted, is straightforward. And actually, the graph, I guess, is the curve. The actual graph is the curve, not the straight line. The straight line is just a connection between the 2 points P and Q. So the actual graph itself is the curve that curves that way. Okay, so far so good. If we were asked to take a gradient of this graph, we could draw a line through them, and that would be the gradient. And we know from high school or some type of school that the gradient is the slope, and the slope is rise over run. So rise is the difference in the y-axis, and the run is the difference in the x-axis. So if we look at this little equation here, we've got, for the rise, we've got the final position of q, which is f x0 plus h, minus the initial, which is just f of x0. And then we do the same for the x-axis. The final x-axis value is x0 plus h, and then we subtract the original x-axis value of x0. So this is our rise over run. If we look at the denominator real quick, we can see we have x0, and then we have a minus x0. So these two x0s will cancel. I don't know if you need me to actually draw that, but you can see that if we cancel this x0 with that x0, there are no x0s in the denominator anymore. Okay, I've got to toggle between scrolling and writing, so it takes a second. Okay, so we've got this function here. If we let the denominator h approach 0, let's remind each other what h is. H is the separation between these 2 points, essentially. So h is the separation between these 2 points. So literally from here to here is h. Okay, so we keep that in mind. Let me toggle back to scrolling. then as h approaches 0, points Q and P approach each other, right? So at the point where h is 0, then the 2 points are on top of each other. And at that point, we would effectively have a tangent. So when h becomes 0, P and Q touch, we've effectively got a tangent. So this is at h is going towards 0. So it's still the same. It's still the same slope. You can see it's a parallel line, but it's now a tangent. Okay, let's scroll down. Okay, so h approaches 0 as point Q approaches point P. And so the gradient, effectively the tangent here, is the limit of this equation at the limit where h approaches 0. So it's the same equation that we had here, but we impose a boundary condition. We're only interested at the limit of this equation where h just approaches 0. Okay. So essentially, because we're looking at a gradient, we're looking at the difference of the numerator function, which is, this is a difference, right? The final value minus the initial is itself a difference d of the function of position x. And the denominator here is the difference on the x-axis of x values. So that's literally a difference of x's. So we have df of x by dx. And here, this expression is the derivative of the function x. So d by dx of the function f of x is now called the derivative. So that might be new vocab for some of you. And we're taking the derivative of the function with respect to x. Okay, so that's basically what differential calculus, at least this basic example of it, is going to look at. So let's have a look at some more things worth looking at this introductory case. So we say that the derivative of a function x to the nth power is, we take the nth power, we make it a coefficient, and we multiply it by the function to the nth power minus 1. So the derivative of x to the n is nx to the n minus 1. Or using our new notation now from here, this derivative, we say d by dx of x to the n is equal to n x to the n minus 1. And here, the numerator is the differential. So we have the derivative, which is the whole expression. The numerator is the differential. So that's some vocab. Let's look at an example. Let's take the derivative of the differential 3x to the 4th power. So d by dx of the function 3x to the 4. Okay, well, the d by dx only varies things that have an x in their argument. Well, the number 3 doesn't. Because the number 3 has no x, the x is just a separate quantity to the 4th power. We can bring the 3 out as a constant. So for example, this differential here, 3x to the 4th power, the 4 applies only to the x. It doesn't apply to the 3. So we could isolate the 3 as a constant, and then we have x to the 4th power. So abiding by our rule here, we take the 4th power, we make it a coefficient, and then we raise it to the 4 minus 1th power. So it's 3 multiplied by 4, x to the 4 minus 1, which is just 12x cubed. Take another example, the derivative of 5x squared. So again, we can take the 5 outside because it's not, it's a constant that multiplies the x term. So we have a 5, and then the 2 becomes a coefficient 2, and then x to the 2 minus 1. 5 multiplies the 2, 10. X to the 2 minus 1 is just x to the 1. which is just x. What if we have the derivative of a constant? Well, the derivative of a constant actually doesn't have an x in it, right? So we can put a dummy x back, but just put an x to the 0. Why? Because x to the 0 is 1. In fact, remember that any number to the 0th power is 1. So x to the 0 is just 1. So by multiplying 7 by x to the 0, it just returns 7 again. So I haven't changed anything. Okay, so I do the same as before. I bring the constant 7 outside as a coefficient, and then I do my, I applied the derivative to the x term. Well, the coefficient 0 is going to come down. Sorry, the power 0 is going to come down as a coefficient. And then I have 0 minus 1, so it's going to be 7 multiplied by 0x to the negative 1th power. Well, the multiple of a 0 just returns 0 overall. Okay, so there's some introductory examples. Okay. What if we have the sum of terms? Well, you can just apply the rule that you've seen so far to each summand. So apply it to the 2x3 term, the 4x squared term, the 7x term, the 2 separately. Okay, so let's look at the derivative of the first term with respect to x. So we've got the 2x cubed term, 2 comes out, 3 comes down as a coefficient, and then we raise it to the coefficient minus 1th term. 2 3s are 6, 3 minus 1 is 2, so we have 6x squared. Again, we take the 4 outside, the 2 comes down as a coefficient, x to the 2 minus 1, 2 4s are 8, and then we have 2 minus 1 is 1, so it's 8x. Constant, I think we've just seen this exact example. Oh, no, we didn't. Sorry, it's got an x here. We saw an example with without an x. So this is 7x to the first power. So the 7 comes out as a constant. We have the 1 comes down. So I haven't written it, but it's because it's just the number 1. So this 1 would come down as a coefficient 1, but then it's 1 minus 1, which is 0. So it's 7 multiplied by, so it's 7 multiplied by x to the 0, which is just 7 by 1, which is just 7, right? Which is just a constant here. Okay, so once you've got all of each summand separately, you can just, oh, we've got the constant 2. The constant 2 is going to return a 0 for similar reasons to the above example. Once you've got them all, you can just add these values back. So we have a 6x squared term, an 8x term, a 7 term. Obviously, we don't have to add a 0, and that's our final answer. Okay, so that's pretty basic. This is a little bit less basic, but not really. Partial differentiation. This is going to be used a little bit in Gen Chem. Certainly, the more you understand it, the more you'll understand what you're doing. And it's essentially where you change the way the D looks. We have this curly D to represent partial differential. And basically, that means that there's more than one argument that can vary. So for example, if we have a function of 2 variables, x and y, then I can look at one differential at a time. One derivative at a time. I can look at the derivative with respect to x while I fix y, keep y constant. And then I can look, keep x constant and look at the derivative with respect to y. Okay, so there's more than one part, so I can look at one part at a time. So here's an example. Let a function of x and y actually equal 2x squared plus 3xy plus 2xy squared. So each term, because it's dependent on 2 variables, whether or not it comes with the term, so here the first term just has an x, but it has no y. I'm actually going to put the y in, but put it to the 0th power, so it just becomes the coefficient 1. So if I'm looking at x and y, I'll make sure every term has an x and a y. So the first term now has an x and a y. The second term already has an x and a y. And the third term already has an x and a y. We're going to look at one term at a time whilst keeping the other term fixed. So arbitrarily, doesn't matter which order you do it in, I'm going to keep all terms y constant initially. Okay, so which would be something like this. This is how I'd write it. Okay, so all terms y as a constant, I can just write as constants. So for this first term, I've got a coefficient 2, so that's just a coefficient 2. Then I'd take the derivative of x squared, so that this squared symbol comes down to give me 2x to the 2 minus 1, which is just 2x. And then y to the 0 is just 1. Okay, so 2 multiplied by 2x multiplied by 1 is this first term. Second term, I have 3x. Well, the 3 comes out as a constant. Then I have x to the first power. I have x to the first power. Well, that 1 now just becomes a coefficient. So it becomes 1 x to the 1 minus 1, which is just 1 x to the 0, which is just 1. And then I have x to the 1. I have y to the 1, which is just y. So the whole thing becomes 3y. And then finally, my last term, this 2x, again, I can take the 2 as a constant. Then the x is actually x to the first power. That 1 comes down as a coefficient, so it's 1x to the 1 minus 1, which is 1x to the 0. X to the 0 is just 1, so it's just 1. So it just multiplies my coefficient 2 by 1, so I've just still got the coefficient 2. And then x squared is just x squared because I'm keeping all my, y squared, what's wrong with me? Y squared, that's not an x, that's a y. Y squared is just written because I've held all my y terms constant. So 2 multiplied by 2 is 4, so I've got 4x, 3y, 2y squared. So this is the partial derivative of the function with respect to x while keeping all y terms constant. Then I have to exchange the favor, keep all x terms constant, and take the partial derivative with respect to y. Okay. So it looks like I've rewritten the original equation here. So remember the original equation here was 2x squared, 3xy, 2xy squared. So 2x squared, 3xy, 2xy squared. And again, I put that y0 in because there wasn't originally a y term. I'm going to keep all the x's constant now. So you see they don't change because I'm looking at the derivative with respect to y. Well, for y0, y to the 0th power, the 0 comes down as just the coefficient. So that's 0. For the y to the first power, the 1 comes down, but the y disappears because it's y to the 1 minus 1, which is just 1. So I'm left just with a 1 here. And for this y squared term, the 2 comes down, and it's 2y to the 2 minus 1, which is just 2y. This first term has a 0 as a coefficient, so it's 0. And I'm left finally with, after a bit of scrolling, I'm left with just these two last terms, 3x and 4xy. So in summary, for this equation, this function of x and y, which is equal to 2x squared plus 3xy plus 2xy squared, the partial derivative with respect to x is this. The partial derivative with respect to y is this. Here's just a second example. You can probably do a little bit quicker. Here we have still a function of x and y. We've got 3xy cubed plus 2xy minus y squared. Again, you can solve for the x constant term first or the y constant term first, it doesn't matter, but I'll just randomly solve for the y constant term first. So if y is held constant, you can keep all of the y's isolated. So let's keep everything that's not a y as a constant. So 3y cubed, and let's keep the x alone because it's just x. 2xy we can write as 2yx because they the associative, I think, is probably the right representation. You can flip the order. Or they commute, probably commute is probably the right word. Okay, so we can have the 2y as a constant, leave the x alone. And here, there is no x, so we can put in a dummy x to the 0th power. So now every term has an x and a y. Keeping all the y terms fixed, I've got x to the 1st power, so that becomes 1x to the 0th overall, which is just 1. Likewise, for this term, it just becomes 1. And then finally, it becomes 0x to the negative 1, which is just 0. That 0 destroys this term because it multiplies it by 0, which returns 0. And I'm left with 3y cubed plus 2y as my final answer for that derivative. Similarly, we can go at it again, holding all x terms constant and taking the derivative with respect to y. So again, I'll keep all the x terms constant and I'll expose the y. So 3x is just written as a constant, 2x is a constant, x to the 0th power a constant. Y cubed becomes 3y squared. Y to the 1st power becomes 1y to the 0th power, which is just 1. And then y squared becomes 2y to the 1st power, which is just 2y. No terms cancel here. I don't have a 0 coefficient. So I have 3 multiplied by 3 is 9, and then xy squared. 2x1, so it's just 2x. And then this bracket is a 1. It's x to the 0, it's just 1. Multiplied by 2y, which is just 2y. So in summary, here we've got the derivative with respect to x, the derivative with respect to y. Now, what am I trying to show you here? Oh, yeah. If you wanted to write this down, we can literally just add both terms. So I've just shown you a couple of examples how to solve for one at a time. So take the derivative with respect to x while keeping y fixed as you vary x, and then take the derivative with respect to y as you keep x fixed as you vary y. So notice we have these partial d's for the actual argument, and then the statement of what you're varying is a regular d. So this is just how you would write this general expression. And what am I trying to show you here? Oh, yeah, this is just to summarize the two above examples. Yeah, so this is the first example we did, the two terms we did in isolation. You could write them in one continuous equation. And this is the most recent example we did. Again, you could write it in one continuous equation. Okay. Differentials, so we've seen derivatives. Differentials, they can be exact or inexact. This is important in chemistry because when you look at state functions, this is the mathematical way. This is mathematically why state functions are path-independent functions. So in an earlier Gen Chem class, if you've ever come across things like enthalpy and regular state functions, Gibbs free energy, entropy perhaps, or the ideal equation of state is also where you look at state functions. You often just learn the statement, state functions path independent, don't worry about why. Path functions are path dependent, the less useful, don't worry about why. But it's because one is an exact differential and one is an inexact differential. So let's have a look at that so we can understand that a bit better. So this following relationship holds only for exact differentials. So basically what this relationship says is that the order that you do the partial differentials doesn't matter. Okay, so if we have a function of x and y, we can look at the function with respect to x while keeping y constant first, and then we can look at the function with respect to y while keeping x constant second. Okay, so this basically says df by dx y first, and then do df by dy and do that last. This is the opposite way around. And if we have exact differentials, the order doesn't matter. And this would eventually lead us to the understanding of a path function. This is what mathematically this path independence. If the order matters, it's a path function. If the order doesn't matter, sorry, my brain was saying state function, but I guess I wrote down path function, which is just stellar. State function. Okay. We can switch the order, it doesn't matter. So let's, I think I fleshed this out with an example now. So let's have a little look. I think I do, maybe I don't in this one. Actually, it looks like I don't, because I guess I chose to keep my notes shorter than, maybe I'll add a second video at some time where I give you an example of an exact differential and an inexact one. I'll flip the order. You'll see that the exact one, it doesn't matter. You get the same answer. The inexact one, you flip the order, you get different answers. So if this holds, then x and y are states. And if they don't, then it's a path. Okay, so I guess just a statement to be aware of, but maybe a second video will come at you. So here's some basic rules that I think will be useful in general chemistry. So the sum rule, if you have a derivative here, it's with respect to time of two functions f and g, you can look at each of them separately. There's the product rule. If you look at a derivative here arbitrarily with respect to t again of a product, you have to use the product rule, funnily enough. So here you would just essentially ignore one function at a time and take the derivative of the other function. So let's say, and it doesn't matter which you ignore first, let's say we ignore f and then just take the time derivative of g, and then we ignore g and take the time derivative of f. Again, it doesn't matter which order you do first. The chain rule, we'll use it a bit in the notes. Let's say you have a function with respect to, or let's say something is defined as a derivative. There's lots of objects useful in chemistry that are actually defined as derivatives. So for example, let's say you had the time derivative of f, but you actually don't want that. You want the derivative of f with respect to g. Or let's say, actually, this is a better way. Let's say you have this variable, you have df by dg, but you want or you need df with respect to t. Well, whatever you have as a denominator in what you have here, the dg, you can make a numerator and then divide it by the thing that you want. And although mathematically this is incorrect to do this, physically it's not that big of a deal. You can imagine that you have a canceling here. So I'm going to say not really, but it's okay here. So imagine they cancel and then you just got the f by dt. So long as you don't show a math professor this, you won't get in trouble. But this is a useful way to think of it in a physical with physical consequences. Okay, so no other rules I think will be that useful. No other differential equation rules really, at least in this basic stage of chemistry. So let's see some examples. So let's see. Differentiate this function using the product rule. So you've got a function here, x squared plus 6, 2x minus 5. Okay. So we can say we've obviously got a product, that the two parentheses are the products. So let the first function, x squared plus x, let's call it a function t, a function of t, or rather, let's call it f of t. And let the second argument, 2x minus 5, be g of t in our previous example. Let's take the derivative of g first. So just looking at the second term here, we have 2x minus 5. So the minus here is just a plus, right? Plus and minus are the same thing. So we can use the sum rule that we saw here, just do one at a time. Okay. So let's do the 2x first. So we've got the number 2, you can just keep alone. And then we've got an x to the first order. So that just brings down a 1 coefficient. So we've already got the 2 from here. The x to the first order brings down a 1. And then we take the x to the 1 minus 1. And then the second term, the constant 5, we can say it's 5x to the 0. So then the 0 comes down, and then we put the 5 there because it's already there, and then x to the 0 minus 1. So that coefficient 0 kills that second term. So we just have the first term. Well, it's just 1 multiplied by 2, which is 2. And then x to the 1 minus 1 is x to the 0, which is just 1. So we've got 1 multiplied by 2 multiplied by 1, which is just 2. Let's take the derivative of the first term, this x squared plus 6. The 2 comes down as a coefficient, and then we have x2 minus 1. And then the second term, 6, same as the previous example, the 0 comes down. The 0 comes down because we have to insert an x to the 0th power. So the 0 comes down, and then we have 6x to the 0 minus 1. But the 0 came down, so we've got a coefficient 0, so it kills the whole term. The term that survives is 2x to the 2 minus 1, which is 2x. So we just write 2x. So writing the whole thing out now, using our sum rule, we have yes. So we're now going to use the full product rule. So let's ignore the first term, x squared plus 6. We write just x squared plus 6. And then we write the derivative of the second term, which is this coefficient 2. And then we ignore the second term, which is 2x minus 5. And then we multiply it by the derivative of the first term, which is 2x. So now we can see we just have to multiply everything here by 2. So we've got 2x squared plus 12. And then in the second term, we've got 2x multiplied by 2x, which is 4x squared. And then 5 multiplied by 2x is 10x. then we can just clean this up a bit. We've got 2x squared plus 4x squared, that's 6x squared. And then we've got minus 10x here, and then we've got the plus 12 over here. All right, so that's an example of using the product rule and just getting your hands dirty with some of these rules. Here's a quick example. Right, we're not too much longer in this video now. Here's a quick example of using the chain rule. So we have a function y is the square root of 3x plus 1. So we've got a function of g of x. So let the function of x be the root of x, and then let g of x be the thing that's rooted. So let g of x be 3x plus 1. So we've got our two functions there. So if you read this backwards, you would take 3x plus 1, and then you take the square root. So you can see where these two separate functions have come from. Okay, so then df by dg is d by dg of f. Now we already said that f is the square root of x. Well, square root just means raised to the half power. So the function square root of x is just x to the half. We know how to handle that, right? The half just becomes a coefficient, a half, and then we raise x to the original exponent a half, but we subtract 1. So it's a half x to the half minus 1, which is negative a half. Negative a half just means 1 over. So instead of a half x to the negative a half, we write a half 1 over x to the half, which is just a half 1 over square root of x. We take the time derivative of g of x, where g of x, we said in our statement here, was 3x plus 1. So basically, we're going to use the sum rule again. So the coefficient 3 can just stand alone. We're only looking at, we know that x has a time derivative in it. So we can say that the 3x to the first order, the 3 just stays there. The x to the 1 comes down as a coefficient, and we have x to the 1 minus 1. Well, that's just 3x to the 0, which essentially is just going to become 3 multiplied by 1, which is 3. And then the second term, the 1 constant here is just a constant. There is no x, so we can say it's 1 multiplied by x to the 0. The 0 comes down and it kills the term. So we're just left with the number 3. So looking at both of these together now, and here's where you can really see the chain rule. We have that same, again, this is not where a math person would do, but you can imagine df by dt is df by dg, dg by dt, where the dg's can cancel in our little non-consequence minds. And you've got this chain rule. So we've said that it's our first argument here, the 1 over 2, 1 over root x, where x was this first term, 3x plus 1. And then our second term multiplied by our second term we said was 3. So which the whole product now is just this term over here. Okay, let me clear my little scribbles. Okay, so that's some basic differential calculus just to whet your beak. Let's look at some basic integral calculus. So again, not a 3-semester sequence in calculus, not needed in general chemistry, but just a feel for some basic uses of the topics. So integration is essentially the reverse of differentiation. So we saw earlier that the derivative with respect to x of x cubed is 3x squared. then reversibly, the integral of 3x squared is x cubed. So they reverse each other. So you can always check if you've done something right by trying to do the opposite argument, see if you return. So the integral of x squared is x cubed over 3. So let's see. And yeah, so we can basically see another example here. The integral of x squared, here's how you'd write it. So here the integral, let me annotate something here. So this integral is this term here. Now, historically, I believe this was invented by Newton. And this symbol is actually an oldie English letter S. And the S here we can use to help us remember. It refers to sum. So I'm going to sum between limits, which we're not at limits yet, but between two extremes, I'm going to sum all of my x squared terms as x changes. So you have to sum over a differential. So here, no, not a differential. You have to sum over a varying quantity. So here my varying quantity is dx. So therefore I'm summing x squared over dx. So let's see a basic rule for that. So in general, the integral or the sum of x to the nth power as x itself varies is x to the n plus 1 over n plus 1. So now you can see where this x cubed over 3 came from. We've got x to the 2 plus 1, which is x to the third power, over 2 plus 1, which is 3. Okay, and it works except for n equals -1. There are some things to be careful of with integration, though. You can integrate with or without constants, and you would never know. So cautiously, we always know that could be a constant term there. And sometimes in physical applications, there is no constant. Sometimes there is. Sometimes we can make the constant disappear. Sometimes the constant has no physical manifestation. But we always have to know that we always have to ask the question, is there a constant? And if so, is it meaningful physically? So let's have a look. Constants cause problems. Let's say you have this derivative here, d by dx of the argument x cubed plus 1. We know that these constants disappear. So let's just look at the x cubed. That becomes 3x squared. So, okay, that looks straightforward. However, if I change the constant from 1 to 2, and I ignore the 2 again, this would give me the same derivative. So these constants are causing problems because I can't take the derivative and get a different value. If I took something like this, though, without a constant, just 3x squared, then I would write oh, no, sorry. This is this 3x squared. If I try and go back again, that's what I'm doing here. If I try and go back again, so I've got the derivative. Now let's take the integral of the derivative to get the original argument again. So I take the integral of the argument 3x squared as the x changes. And then I get the value 3 as a constant. This 2, I add 1 to it, so it becomes x cubed. And then I divide by that 2 plus 1. So it becomes 3x cubed over 3. So notice that I don't get back to either one of my original arguments. I just get 3x cubed over 3, which is just x cubed. So this is what I mean by constants can cause problems. We can't track information about the constant term. So to represent that, it's common to just write a capital C to represent, hey, there's a constant here. I have no idea what it is, but it's a constant. So we can just say the integral of 3x squared as dx is equal to x cubed plus a constant. The constant might be 0, but it might not be 0. So don't shout at me if I've told you there might be a constant there. Okay. I think this might be the last page that I wanted to, yeah, so this is like half a page now. We're almost there. In chemistry, the integral in question is often the definite integral whereby the constant of integration cancels. So let's see an example. So for the most part, in general chemistry, these constants are of no consequence. They disappear. But we have to know that there's something in the background disappearing. So let's look at the integral between the limits 2 and 1 of the argument x cubed as dx. Okay, so this tells us to calculate the integral of x cubed between the limits 2 and 1. Okay, so the first term, we have x cubed, so we would add 1 to the cube, so we have x4 over 3 plus 1, so it's x4 over 4, plus a constant, so it's that entire term between the limits 2 and 1. That's what we're asked to do. So that would equal, well, when we take the bigger limit and we subtract the smaller limit from it. So x when between the limits 2 and 1 means take x when it's equal to 2. So we just insert a 2 here, and then we subtract the same argument when x is equal to the lower limit 1. So it becomes this argument here. So 2 to the 4th power is 16. So we have 16 over 4 plus a constant. And then 1 to the 4 is just 1. So we have 16 over 4 plus a constant, minus 1 over 4 plus a constant. This minus here, though, makes this plus a negative. So we actually have a positive constant minus the same constant. So the constants cancel. So this is what I mean by these constants. We can often get away getting rid of them. The constants cancel. So we just have 16 quarters minus 1 quarter, which is 15 quarters. And that, I believe, is all I wanted to add to this video, which again, it's optional for my students. And it's just a basic taste of some differential and integral calculus that will help you understand some of the kinetics notes I just posted and will be useful in some of the other notes that we'll see in general chemistry this semester.